My screen visible? Okay. Okay then. Good evening, everyone. So today is the third week for the tutorial, and today we will be discussing a different kind of energy harvesting technique. It is a new kind of energy harvesting technique which is trending currently among the researchers. There is a lot of research. It is not that explored. It is not that known to people yet. Researchers are currently researching, currently working in these energy harvesting techniques. Basically, its origin started in the year, the research on this was started by one of the scientists, Professor Zhongling Wang, who is currently working at Georgia Institute of Technology, and he started working in this field in the year 2012. So 2012 he started. So it is not a very old technology. So it is not that exhausted yet. It is not that much known to people. So we'll be getting a gist of it today. Okay. So the technology, the energy harvesting technique that we are going to study today is nano generators. Okay. So basically, what are nano generators? So nano generators are basically it is a type of device which converts mechanical energy or thermal energy as produced by small scale physical change into electricity. Basically, it means that it converts small amount of energy into electricity. For example, when you rub your hands, okay, when you rub your hands, there is some kind of frictional force between the hands, some kind of electrostatic force which is generated between the hands. So it is very small in quantity, very small amount of electrostatic energy which is generated while rubbing your hands together. But that small amount of energy also, if you are able to convert it into electricity, then that kind of devices are that work is done by devices called nano generators. Okay, so basically, converting very small amount of energy, like energy, if you suppose put pressure or while walking, you put pressure on the ground, that pressure can be converted into electricity. If that pressure can be converted into electricity, or if suppose you are hot water is flowing through a pipe. Suppose hot water is flowing through the geyser pipe, so you are getting hot water, but some amount of heat is getting dissipated at the surface of the pipe also. Okay. So, but that is a very small amount of heat energy, but still, if that heat energy you could convert them into an electricity or usable power, then that can be done using nano generators. Okay. So basically, it converts mechanical energy. Mechanical energy, you can say either by putting pressure or by bending or by stretching or by a small amount or a small amount of vibration. All those type of energy, and then thermal energy, like energy that thermal energy or electromagnetic force. All that can be, if it is wherever it is produced in very small quantity, if that can also be converted into electricity, that is done through nano generators. Okay. So the discovery of nano generators was it is considered one of the top 10 world discoveries in science according to academicians of Chinese Academy of Science. Okay. It is considered as a very top notch discoveries, and it is as I told, it is not very old technology. It has been current it is currently explored by the researchers. So it is not a very old technology, and if exhausted properly, if researched properly, it could be the future of energy. Okay. So there are various type of nano generators depending on what kind of energy is getting converted into electricity. Okay. So for example, there are piezoelectric nano generators, triboelectric nano generators, pyroelectric nano generators, thermoelectric nano generators, electromagnetic nano generators. So all these we will be discussing today. Okay. So coming on to piezoelectric nano generators firstly. So piezoelectric materials are basically those which have ability to generate electric charges when subjected to a mechanical pressure. Okay. So if suppose you apply a mechanical pressure and by that mechanical pressure electricity is generated, mean if you could convert that small amount of mechanical pressure into electrical charge or electrical energy, then that material is called piezoelectric material. Mean it is not like all the materials will show that property, or it is not like that all the materials will can easily convert mechanical pressure into electricity or electrical charge. Only specific kind of materials with specific properties are able to like convert this mechanical pressure into electricity. We will be talking about all those materials, what are the properties required. Okay. So the piezoelectric materials are the materials, they have the ability to generate electric charge when subjected to a mechanical pressure. Okay. Through piezoelectric effect. So the word piezoelectric, it comes from a Greek word. Piezo means pressure. Okay, to press means to simply if press. Like if you while walking, you put pressure on the ground. That amount, that pressure can also be converted if you could integrate some kind of small device into the shoes, so that while walking, the pressure that you are putting on the ground, then that device will convert that pressure into electricity. Not very large amount of electricity, but if possible a small amount of electricity that could that could power up your wearable devices. For example, at least that much, if suppose that device integrated in your shoes can convert the pressure you are putting on the ground into electricity, and that electricity can be used to power up your wearable watches or power up your implantable devices. Okay, so that amount of electricity would be like a good idea. Okay, a more sophisticated definition of piezoelectricity was given by Caddy, that is the electric polarization produced by mechanical strain. Basically, what is done when the mechanical strain is produced, charge within within the piezoelectric material, mean if they have equally distributed charge, like positive or negative, and if we apply a mechanical strain, what happens, these charges get aligned, they form dipoles. Okay, positive charge moves to one side and negative charge moves to other side, and due to that polarization itself, if you attach a external load in the circuit, if you attach a load in the external circuit, then you can extract that electric charge using that polarized effect in the material. Okay, that is not possible in all materials. In some different some type of materials only that is possible. Okay, so the phenomena of piezoelectricity was discovered by Curie brothers in 1880 during their investigation on the pressure effect of pressure on the generation of electric charge. Okay. So what is piezoelectric effect? Basically, there are two types of piezoelectric effect: the direct piezoelectric effect and converse piezoelectric effect. So what is direct piezoelectric effect? That is when electric charge is generated as a result of mechanical stress applied to the crystal. Mean it is possible that you apply pressure and you get electric charge. It is also possible that if electric charge is if you apply electric field to your crystal, then a strain is generated. Okay, mean vice versa is possible, that if you apply strain, then electric charge will be generated, that also is possible. And if you put your crystal in an electric field, and that may generate a mechanical strain to into your crystal, that is also possible. Mean this is the vice versa. So the direct piezoelectric effect is when electric charge is generated as a result of mechanical stress applied to the crystal. But when a strain is generated as a result of electric field applied to the crystal, that is the opposite of direct piezoelectric effect. Okay. Theoretically, these two effects are described by two basic equations which relate the elastic variables stress and strain to the electric variables field and displacement. So these are two equations for direct effect and converse effect which connect the mechanical variables, that is stress and strain, to the electric variables, that is field and displacement. So these are the two equations, okay, where S is the elastic compliance and epsilon is the dielectric constant. Okay. So what are the parameters which affect the performance of any piezoelectric material? So these are some of the parameters which affect the performance of any piezoelectric material. That is the electromechanical coupling factor, which is K, piezoelectric strain constant D, piezoelectric voltage constant G, mechanical quality factor QM, electric loss 10 delta, and dielectric constant epsilon, which is also called relative permittivity. Okay, so we will be discussing all these factors in detail. So the first one is electromechanical coupling factor K. So what is electromechanical coupling factor? It is basically efficiency. Mean it is an indicator of efficiency basically, as we can see here, which is given by with which a piezoelectric material converts electrical energy into mechanical energy or mechanical energy into electrical energy. So basically, if you are converting mechanical energy into electrical energy, that is direct piezoelectric effect. So the definition would be K square equals to mechanical energy converted to electrical energy upon input of the mechanical energy. Basically, the output to input. So the amount of mechanical energy, how much mechanical energy gets converted into electrical energy, to the amount of mechanical energy you input. Okay. So basically, output to input ratio it is. Whereas in the opposite case, it will be electrical energy converted to mechanical energy to amount of electrical energy that you gave. Okay. So it is simply efficiency. It is given denoted by Kij, where I is the electric field direction and J is the longitudinal vibrational direction. A typical piezoelectric ceramic can convert 25 to 50% of the energy delivered to it in one form to the other depending on its structure. Depending on the different type of piezoelectric materials, the efficiency can vary. That is, as here it is showing that piezoelectric ceramics can convert 25 to 50% of the energy delivered to it into the output. Basically, if you are giving suppose 100 amount of mechanical energy, then you can get 20 to 50 amount of electrical energy. Okay. Now, simply it shows that a high K value is desirable for efficient energy conversion. So, for a good piezoelectric material, the for a material to be a good piezoelectric material, then it should have high K value. Okay, high electromechanical coupling factor. The second factor is piezoelectric strain constant, that is D. So, piezoelectric strain constant is the ratio of the electric charge generated per unit area and an applied force. Basically, that is the charge density upon applied stress. Okay. In case of direct piezoelectric effect and in case of converse piezoelectric effect, it is the strain developed upon applied field. Basically, the electric charge generated per unit area upon field. Applied stress means that force upon area. Okay. So basically, it is the charge density, that amount of charge, electric charge that we get upon the to the area to which the mechanical force is applied. Okay, and the formula for this is kx under root epsilon naught epsilon s to the power e, where K is the electromechanical coupling factor, that is the efficiency. Epsilon naught is the relative permittivity of free space. Epsilon is the dielectric constant of relative permittivity, and S to the power E is the compliance, which is a constant which with the value of 10 to the power minus 12 meter square per Newton. So it is generally denoted by Dij, where I is the induced polarization direction and J is the stress applied direction. Okay. So D is an important factor of a material suitability for strain dependent applications. Basically, if you are using a material for actuator based applications, then this D value is a very important indicator. Next is the piezoelectric voltage constant, that is G. Piezoelectric voltage constant is the ratio of electric field produced to the mechanical stress applied, and it is expressed in volt meter per Newton. So basically, it is the field developed to the applied mechanical stress or strain developed to the applied charge density. Okay. It is generally denoted by Gij, where I is the induced electric field direction and J is the stress applied direction. And J is an important factor for assessing a material suitability for sensing application. So depending on the different kind of applications, so here for the actuator application, this D factor is important. For sensor application, this value is important. Okay. So depending on different kind of applications, what factor is the key factor to determine if a material can be used or not? There are different factors. Okay. Coming on to the next factor, which is the mechanical quality factor. The mechanical quality factor, it is defined by this formula Qm equals to 2 pi f UE by PD, where U is the stored mechanical energy of the material, that is the inherent mechanical energy which is already present into the material before charging basically, or before applying any mechanical stress or strain to the material. PD is the power dissipated and 2 pi f is the angular frequency. Piezoelectric material with high QM is desirable for piezoelectric nanogenerators. Okay. Then electrical loss tan delta, the dielectric loss factor, which is defined as the tangent of the loss angle. The loss factor is inverse of the mechanical quality factor. So the loss factor tan delta, it is 1 by QM. And dielectric constant, that is the relative permittivity. The dielectric constant is defined as the ratio of the permittivity of the material to the permittivity of free space. Okay. So this is the formula for dielectric constant. So these are some of the factors which needs to be taken care of before you choosing a material to develop a piezoelectric nanogenerator. So these are some of the piezoelectric constants of different materials. These are some of the piezoelectric materials: PZT4 or PZT4, PBNBO3, PVDF, LiNBO3, aluminum nitride thin films, PMNPT. So different, all these materials have different, they have given the values of all these factors, parameters for all these materials for comparison and to see what kind of which material will suit your application the best. Okay. Now coming on to piezoelectric nanogenerators. A piezoelectric nanogenerator, which is an energy harvesting device which is capable of converting external mechanical energy into electrical energy via action via nanostructured piezoelectric material. Okay. So now we will be studying basically the working of piezoelectric nanogenerators, different types of nanogenerators, what makes them different, what is the difference in each of them depending on the mechanism. Okay. So based on mode of operation, this is the piezoelectric nanogenerators. They are basically called PENG in short. So based on the mode of operation, PENG can be divided into firstly the force exerted. If the depending on the mode of operation, force exerted perpendicular to the axis of nanowire, and another is force exerted parallel to the axis of nanowire. Okay. Then based on the structural configuration, they are of three types: vertical nanowire integrated nanogenerators, that is wing; lateral nanowire integrated nanogenerator, that is link; and nanocomposite electrical nanogenerator, that is neg. So we will be discussing each of them one by one. So the first one is the force exerted perpendicular to the axis of the nanowire. Okay. So basically, this is a nanowire. They are considering nanowire as piezoelectric material. Any nanowire, depending on all the uh, piezoelectric material, basically it is. So basically, piezoelectric PENGs are formed like two electrodes will be there. This is electrode 1, electrode 2, and in between both these electrodes, there will be a piezoelectric material will be sandwiched. Okay, so basically, they are crystals or nanowires or nanostructures which are sandwiched between two electrodes, and then we apply pressure over over these electrode. Suppose if we apply pressure like this, or if we apply pressure laterally, then that pressure will be converted by that pressure will induce strain or stress into these piezoelectric materials, due to which the uh, polarization of charges in the piezoelectric material will be there, and in the electric charge will start to flow in the external circuit. So that is the basic mechanism of PENG. So what happens is, when a piezoelectric structure is subjected to external force by the moving tip perpendicularly. Suppose these are the piezoelectric materials, they are aligned straight. Okay, so they are straight between the two electrodes. And if we are applying perpendicular force, mean they are like this, these piezoelectric materials are like this, and we are applying force here, okay, from in perpendicular direction to the axis of the nanowire. So what will happen? The mean the whole nanowire will be the will ex- mean will be distorted. Okay, will be in strain. Whole nanowire will be in strain. So how the deformation occurs throughout the structure, because if the nanowire is like this and you are applying pressure here, this complete nanowire will move like this, or it may bend, or it may, if it is like not very ductile, then it may like bend, or mean in it may form an arc if it is ductile, and if it is not that ductile, then it will like move in this direction, and then it will form an angle with the base. Okay, so basically the deformation in them occurs throughout the structure. So what will happen? Suppose if pressure is here, then this portion, upper portion is is in tension, and this lower portion is in compression. So the stretched part with the positive strain, so this will be in positive strain, and this portion below part will be in the negative strain, will exhibit the positive electrical potential, whereas the compressed part will, with the negative strain, will show the negative electrical potential. The ohmic contact that is formed between the bottom metal plate and the nano structure causes neutral. So this point, this the point of contact between the lower electrode and nanostructures. This is the ohmic contact. This is called the ohmic contact. So the ohmic contact that is formed between the bottom metal electrode and the nanostructure causes neutralization of the electric field generated at the tip of the nanostructure. So here, due to this deformation, some kind of electric field is generated which moves downward, and it gets neutralized due to this ohmic contact with this electrode. And the Schottky contact that is formed between the top metal electrode and the tip of the nanostructure is responsible for generation of an electric current. So here it will be positive, and here it will be, suppose if it is negative, then when this is in contact with this electrode is in contact, then current will flow in this direction. And if you attach a load here, suppose a bulb or an LED, that will be lighted up. Now coming on to the next, am I audible? Next is the force exerted parallel to the axis of nanowires. If suppose these are the nanowires, and this is the Schottky contact, and this is the ohmic contact, and if these are the electrodes, suppose mean upper electrode and lower electrode, and if you are applying pressure parallel to the axis. So this is the axis of nanowires, and this is the force that is. So if you are applying pressure from parallel to the nanowires, then what will happen? When the force is applied towards the tip of the nanowire, uniaxial compression is generated. So in this case, all these nanowires, they will be in compression mode. So due to the piezoelectric effect, the tip of the nanowire will have a negative piezoelectric potential. So tip of the nanowire here, it will be a negative. If this is negative, then here it will be positive, and if this is negative, it will be positive and it will be negative. So now in the external circuit, current will flow in this direction. Okay. Sorry, current will flow in this direction. Just a second. So when due to the piezoelectric effect, the tip of the nanowire will have a negative piezoelectric potential, and a positive electric potential is created at the other tip owing to the flow of electron from top to the bottom. When the external force is removed, the induced piezoelectric effect instantly vanishes, and the positive potential of the at the bottom tip of the nanostructure is neutralized because of the migration of the accumulated electrons from the bottom to the top electrode of the nanostructure via the external circuit. Okay. So it means basically when the pressure is applied, current will be flowing in the external circuit, and as soon as you release the pressure, the this polarization, that is the negative upward and positive downward, the this polarization of the charges, as soon as you remove the pressure, it will be vanished. They will be like back to the randomization or neutralization of the these charged poles. Okay. Now another is type of tank based on the structural configuration. There are three types. So first one is the vertical nanowire integrated nano generators. So basically vertical nanowire, it is a 3D configuration which consists of three layers. Basically the base electrode, then vertically grown piezoelectric nanostructure. These are the vertically grown piezoelectric nanostructures, second layer, and third one is the counter electrode. So the piezoelectric nanostructure is usually grown from the base electrode by various synthesizing techniques. So basically it is inherently grown over this base electrode. You take the electrode and you grow nano structures or nano wires, piezoelectric nanowires on the base electrode itself by various synthesizing techniques in the lab. It's not like you externally put, they are basically inherently grown over this uh, surface. Okay. Then they are integrated with the counter electrode in full or partial mechanical contact with its tip. And then pressure, you can either apply pressure here or here, either parallelly to the piezoelectric nanomaterials, or perpendicularly, that is depending on the requirement. Okay. Next is the lateral nanowire integrated nanogenerators. So here, the growth of the nanowires is lateral. Okay, so suppose this is one electrode, this is second electrode. So nanowires are grown between the two electrodes laterally. Okay, so base electrode, top metal electrode, and the laterally grown piezoelectric material. So it is not grown vertically, it is grown laterally. So the first metal electrode is used for establishing Schottky contact, whereas the second metal electrode is used for responsible for the creation of ohmic contact. The voltage generated by a link can be increased by arranging a large number of links in series. So as many, if you want to increase the voltage generated by a link device, then you can increase as many number of links, you can arrange as many number of links in series as you want depending on your requirement. Okay. So now another one is the nano composite electrical generator. So basically it is a NENG, it is a three-dimensional structure where metal plate electrodes are there. So these are two metal plate electrodes, vertically grown piezoelectric nanostructures. These are the vertically grown piezoelectrically nanostructure, and polymer matrix. And this area between, it is the polymer matrix. Okay. So basically here, what is the difference here? The distance between the nanostructures, we have filled them with the polymer matrix. Why? So that is basically the polymer matrix fills the space between the piezoelectric nanostructures. It was shown that NENG has a higher efficiency compared to the original nanostructure configuration, which ZNO nanowire will be bended by an AFM tip. So basically, it provides an energy source with higher sustainability. So basically, if we fill nano polymer matrix in between this, what happens? It basically increases its mechanical strength. So if the nanostructure it is not that ductile, or if it is brittle, then also if the spacing between them is filled with the polymer matrix, then it will provide an additional mechanical strength to the piezoelectric device. And chances of failure of the nanostructure, if they are not like ductile, if they are brittle, then chances of its failure will be less. Okay. I mean, if suppose this nanostructure, if this nano wires, they are brittle in nature. So if you will apply pressure, they can easily break. But if you fill these areas with the polymer matrix, then the mechanical stress absorption of these nanostructures, nanowires will be increased. Okay. So the materials used in nano, coming on to the materials, which materials you can use in the piezoelectric nano generators. So basically, the mechanism of power generation mainly relies on electromechanical properties of the material and formation of a Schottky contact between the tip of the nanostructure and the metal electrode. Okay. So it depends on these. It is a combination of these two mechanisms. The piezoelectric semiconductor materials with the wurtzite structure, such as zinc oxide, gallium nitride, and cadmium sulfide, because they exhibit both semiconducting and piezoelectric properties simultaneously. You can use the materials which have both piezoelectric effect also and semiconducting effect. If they both have together, then that is also a benefit. Then inorganic materials have a limited number of applications because of their low formability and brittle nature. If there are various inorganic piezoelectric materials are also there, but they are less used because of their less their brittle nature. They can easily break. And sometimes polymers, mostly PVDF, that is polyvinylene difluoride, are used as an alternate material in applications in which a lightweight generator design is required. If the lightweight pengs are required, then polymers are basically uh, used, because polymers are very lightweight. So based on the unit cell, there are three main groups of piezoelectric materials. Okay, so there are basically three types of piezoelectric materials which are famous right now. One is the perovskite groups, another is the bismuth layer structure group, and the third one is pyrochlore group. So we will be studying each of them one by one. Perovskite group, as I have told you earlier in the solar cells also, it is basically a group which is by far the most important class of piezoelectric materials, having the highest piezoelectric constant. Piezoelectric constant, that is the K value. As I told, that it should have a very good high piezoelectric constant for the material to make a good piezoelectric device, and an immense number of applications where these perovskite materials have. It is basically having a AbO3 kind of formula structure. In the perovskite family, the PZT type ceramics play the leading role. And the structure may be described as a simple cubic unit cell with a large cation on the corners, that is A site, and a smaller cation on the body center, B site, and oxygen in the centers of the faces. So, for example, BaTiO3, PbTiO3, or PbZr, ZR 0.52, Ti 0.48, and O3. So basically, overall, it should form a AbO3 kind of formula. Okay. Another one is the bismuth layer type. So it has a general formula B bismuth Bi2 A x minus ax minus 1 bx and o3x plus 3, that is, it is in short called as bls. This structure can be considered as a layer of perovskite unit cells, infinite in two dimensions, separated by BiO2 two positive layers. Okay. The perovskite layer can have a thickness of one or more unit cells, denoted by the parameter x in the chemical structure. Materials with BLS have a tetragonal symmetry in the high temperature phase. So, for example, it is SrBi2 Ta2O9, Bi2 WO6, PbBi2 Nb2O9. These are some of the bismuth layer structure materials which can be used as piezoelectric materials. Now, third one is the pyrochlore group, that is A2B2O7 type of structure. The pyrochlore structure displays cubic symmetry with a general stoichiometry of A2B2O7. In this structure, A is a large, low valence cation. B is a small, more highly charged cation capable of octahedral coordination. The typical structural markup of A2B2O7 pyrochlore, you just need to memorize this basic general formula, and you can see some of examples of all these groups. The typical structure markup of A2B2O7 pyrochlore, showing the two interlinked structure of blue BO6 octahedral and A2O framework. Oxygen shown as red, this is oxygen, and A side shown in purple. So now coming on to what are the challenges that are faced with this piezoelectric materials, because like as I told that this is a new field, so there are various challenges researchers are currently facing and working on them basically. So the first one is increase of the output power density. As I told you, the power, efficiency needs to be improved. Till now there is not, it is not like, they are not still these techniques, these nano generators are not still commercialized, so they are not commercialized techniques. So to increase or to commercialize them, efficiency needs to be improved. The integration packaging of energy storage unit with the nano generators, as I told, it generates very small amount of energy or very small amount of electricity. So basically, integration of these nano generators with some energy storage device would be a good, would be advantageous, but it is very challenging also. Optimization on harvesting efficiency of mechanical energy from various working conditions. Optimization of electromechanical conversion efficiency through structural design. Basically, optimization of efficiency, harvesting efficiency of these piezoelectric nano generators, depending on the structure design of the piezoelectric materials, or on the working conditions. Then the long-term stability is also a problem. Mechanical strength of these materials is a problem. Chemical stability of the nano generators is a problem. And temperature drift during the sensing process for active self-powered sensors, the integration of active or self-powered system with data processing and transmitting system. So all this needs to be done, but it is basically a challenge right now, and it is currently the focus of researchers. So they are currently working on increasing the efficiency, the durability, then chemical stability, mechanical strength, then integration of these nano generators with different other devices, so that so that its commercialization becomes profitable. Okay. So now coming on to the advantages, Peng is portable and wearable device. It can interface with biological systems also. Can Has a very compact configuration. It is compatible with micro electromechanical systems also, and don't release any harmful gases. Obviously, there is no harmful effluents are there, so it is a very good alternative for energy storage and generation. Then, disadvantage is the brittleness of the piezoelectric materials. Piezoelectric material should be ductile, but it is still not many materials are discovered which are like very good, which are showing very good ductility. Then uniformity in alignment of nanowires. All the nanowires, they should be aligned in a single row, but it does not happen. Like as I told, I mean all they should be straight. But some of if any one of them is supposed like this or like this, then that creates a problem. Need to be protected from water, and durability of the structure is very less. Okay. Now these are some of the applications of the peng. I mean, as I told, if pressure exerted by the shoes on the floor, then in smart homes it can be used, then it can be used in automobiles in different ways, then in machinery, then fluid flow, the pressure exerted by the waves, tidal waves, then that can also be used for the generation of for conversion of that pressure into electricity can be generated. So there are various applications which basically it's not like all of them are generated, all of them are like usable, but they are in the process. Okay. Now coming on to the second type of nanogenerator, that is triboelectric nanogenerator. So basically small size electronics operate at ultra low power consumption, can be powered by energy harvesting from our living environment. How so? It is saying that we can generate very small electronic devices which can generate ultra low power, which can take ultra low power consumption, and it can like generate energy. I mean, we can generate energy from all around our environment in small things like, as I told, pressure of our walking, or like simple tapping on your hands, or like basically pressure of water, or while jogging, if you're jumping, all those pressure can be converted into electricity or power. Not very large amount of power, but into amount of power where small amount of power is required, there you can use this kind of power. Okay. So a triboelectric nanogenerator is an energy harvesting device. It converts the external mechanical energy into electricity by conjunction of triboelectric effect and electrostatic conjunction induction. So basically, here triboelectric nanogenerators are basically focusing on converting the forces like by conjunction of electrostatic force. Mean if for example, when you rub your hands together, then charge electrostatic charge is generated. If we can convert that charge into electricity, that is done by the triboelectric nanogenerators. Okay. So it is a new technology, new type of nano generators, which was demonstrated by Professor Zhongling Wang Group at Georgia Institute of Technology in the year 2012. Okay, so here we will be focusing on triboelectric nano generators. So it is a contact-induced electrification in which a material becomes electrically charged after it is contacted with different material through friction. So basically, if two different materials comes into contact and they both get different charges, okay, on getting contact, they get different charge through friction. When two different materials coming into contact, charge move from one material to the other to equalize their electrochemical potential. So this transferred charge can be electrons or maybe ions or molecules. When separated, some of the bonded atoms have a tendency to keep extra electrons and some have a tendency to give them away, possibly producing triboelectric charge on surfaces. Basically, if you rub them, then one surface will get positive charge, other surface will get will get negative charge. And if you attach, if you connect them with an external circuit, then you can basically light up a LED or light up, generate electricity using that charge. Okay. So materials that usually have strong triboelectrification effect are likely less conductive or insulator. So basically here, if the material needs to have good triboelectric effect, then they should be less conductive, or less conductive, or insulators are also fine. Okay. So coming, let us understand it in a very layman language. For example, if you have a balloon, the charge in the balloon is completely balanced. It is randomly distributed. You can see positive, negative, randomly distributed. Equal charge, but randomly distributed. If you bring a charged metal rod near to it. If suppose the rod is charged, it is negatively charged, then what will happen? The negative charge of the balloon will automatically move away from the rod, and positive charge will move towards it due to the, as we know, opposite charge attract. And as soon as you remove the charge rod away, then the balloon gets neutralized again. But here it is not neutralized, it is polarized. Okay, two different poles, two different charge poles have formed. But if you remove the like external charge, then it becomes neutralized again. At first, the rod has a negative charge and balloon has an equal charge. When the rod comes close to the balloon, electrons in the balloon move away from the rod. When the rod moves away, the electrons in the balloon spread out evenly as before. Okay, so the electrostatic induction is a method to generate static energy in a material by bringing an electrically charged object near to it. So basically, there are various materials which have triboelectric effect. Almost all materials have triboelectrification effect, including metals, polymers, wood, etc. But all of them have different. Okay, so these materials here, they have positive effect when you will rub these materials with another material, they will generate a positive charge, increasing in this order. So this is the most positive, maximum positive charge will be on polyformamide, that is 1.3 to formamide 1.31 to 1.4. And these are negatively charged with the maximum negative charge on Teflon. Okay. So basically, if you use the maximum positive and maximum negative together, then you can make a very good triboelectric nanogenerator, that is 10. Okay. It is in short, it is called 10. So triboelectric nanogenerator is made of two sheets of material that have distinctly different triboelectric characteristics with one easy to mean you need to take two sheets which has one has a tendency to gain electron and one has a tendency to lose electron. Like very easy to gain electron and another has very easy to lose electron. So there are different modes of present in triboelectric nanogenerators. Different types of triboelectric nanogenerators are there. The one which we will be discussing further. The working principle of TENG can be described as a coupling of contact electrification and electrostatic induction. So basically, two materials are brought together. They are brought in contact and rubbed together, or like rubbed together or tapped together, mean they are brought in contact, due to which electrostatic induction takes place. Different mean opposite charges form on the two plates, and that is the main principle of triboelectric nanogenerator. So what happens in triboelectric nanogenerator? So firstly, charge generation takes place. You bring together, rub them together, then charge generation takes place. Then charge separation takes place. If you bring another charge species to near to both the plates, or mean attach a external circuit to it, then charge separation takes place and then charge flow takes place. Okay, so basically for tank, increasing the charge generation can be achieved. How to increase the charge generation? Basically selecting material with large differences in the ability to attract and retain electrons. So basically choosing two materials which has very large difference, like either if suppose we choose the maximum positive and maximum negative, then that is a very good thing. Changing the substrate morphology by surface modification. Apart from that, we can also do the modification of the substrate. We can do the modification of the two electrodes. That can also increase the charge generation. Then enlarging the contact area of the materials. If we can increase the contact area of the both the materials, then changing the environmental conditions such as temperature and pressure. So environmental conditions can also increase the charge generation. Okay. So coming on to different modes. So first one is the vertical contact separation mode. Two dissimilar dielectric films face with each other, and there are electrodes being deposited on the top and bottom surface of the stacked surface. So suppose these are two plates. This is first electrode, this is second electrode. It is positive charged and it is negative charged. Okay. So what happens when these are vertical contact is done, like mean it is tabbed. Suppose vertical contact, when you put one plate over other and you apply a little pressure, mean pressure and release, basically like tapping of your hands, clapping basically, kind of thing. Okay, so one is constant and you are like tapping the upper plate over the lower plate, So that is the vertical contact separation mode. So contact and then separation, pressing, releasing. Okay. So that is, this mode is basically that. So you are pressing. So what happened? Charges are separated. Then you are releasing. And in the case of releasing, what will happen? During releasing, the current will generate flow in the for the balancing, current will flow in the external circuit and the LED will be lighted up. Okay. So that takes place continuously. In this, this was a video. Here it is not playing. So basically, he's tapping this. This is one plate, and this second plate is in his is in the hand. So it is he's tapping this second plate over first plate, and when the contact is there, LED is lighting. A physical contact between the two dielectric films create oppositively charged surfaces. Once the two surfaces are separated by a small gap under the lifting of an external force, a potential drop is created. Once the gap is closed, the triboelectric charge created potential disappears, the electron flows back. Okay. So when it is contacting, oppositively charged, opposite charges are created. When the two surfaces are released by lifting of an external force, potential drop is created. So this is the potential drop which is created. And once the gap is closed, then again when it is pressed, the contact is made, the triboelectric charge created potential. So this, when it is again pressed, this potential drop causes the flow of current in the external circuit to balance the charges, and that's why the LED gets lighted up. Now coming on to the lateral sliding mode, when two dielectric films are in contact, relative sliding in parallel to the surface creates triboelectric charge. So here, not that was the vertical contact. Now it is lateral contact. So basically sliding. So one film, like one electrode is constant, this is constant, and this is slided over, like lateral sliding of the one electrode over other. So here it is slided over the other. Okay. So due to that contact, polarization takes place, and and the current flow in the external circuit, polarization takes place, then potential difference forms, and then when it is connected in the, when the external and the current flows in the external circuit, and LED lights up. This polarization drives the electrons on the top and bottom surface of the electrode to flow in order to fully balance the field created by the triboelectric charge, and a periodic sliding apart and closing generates an AC output. The sliding can be a planar motion, a cylindrical motion, or a disk rotation. Okay. So the sliding, it is not like it, this is a planar sliding. It can be like one, this is the one electrode, and other electrode is cylindrical over it. So it can also be like motion of this, you take this rod out and in, that can also be, or you can rotate this rotate this outer cylinder with respect to the inner cylinder, that can also be. So this lateral sliding, it can be either like planar sliding or rotational sliding, any kind of sliding can be comes under this lateral sliding mode. Okay. Now other is the single electrode mode. In this single mode, electrode on the bottom part of the tank is grounded. So this bottom electrode, it is grounded. If the size of the tank is finite and approaching or departing of the top object from the bottom, one would change the local electrical field distribution. Here, electron changes between the bottom electrode and ground to maintain the potential change. This energy harvesting strategy can be in both contact separation mode and lateral sliding mode. So here in this case, the only difference is one electrode is grounded. Okay. So in that case, this single electrode mode is used. You can either like do the sliding of this electrode, or you can simply do the tapping. It can be, this method can be done in both the cases. Okay. Then other is the freestanding mode. In this mode, we make a pair of asymmetric electrode beneath a dielectric layer. So here two electrodes are there, two Suppose this is a single electrode and two different positively charged electrodes are present. And if you move this negative charged electrode near to mean both of these, then both mean you slide it from here to here, then firstly this will attain positive, then this will attain positive, and if it is in the between, both of them will attain positive charge. So the object approaching to or departing from the electrode creates an asymmetric charge distribution in the media. It causes the electron to flow between the two electrodes to balance the local potential distribution. This is a good approach for extending the durability of the tank. Okay. Coming on to difference between what is the difference between piezoelectric and triboelectric. So difference is, in the case of piezoelectric, only bending and vibration force is there. I mean, you are applying a vibration force or you are applying a pressure, then that is converted into electricity. Whereas in the case of triboelectric force, pressure is also there, vibration, rotation, sliding. You can do any kind of, any of these forces can be applied, and that can be converted into electricity. Then different kind of materials are used in both. Okay. And then the output here also, efficiency of the piezoelectric nanogenerators is 25 to 50%, whereas triboelectric nanogenerator is it is a bit higher, that is 30 to 60%. Output in the case of triboelectric nanogenerators is quite high compared to the piezoelectric nanogenerators. And applications, in case of PENG, it is body implantation devices, wireless sensor modes, wearable devices, and in the case of TENG, it is self-powered devices and wearable devices. Coming on to the advantages and disadvantages, TENG gives high voltage and low current output. It has high efficiency at low frequencies. It is low cost and low weight, and it has multiple working modes, and it has diverse material choices. Whereas disadvantage, protection of tank surfaces from environment is difficult task. It does not have long durability and stability. And precaution should be taken when tank is combined with other energy harvesting devices. And these are some of the applications in which different tanks are used. I mean, tank can be used in wearable devices, powering wearable devices, self-powered pressure sensors, then self-powered wearable flexible patch for robotic manipulators, and many such applications are there. Now coming on to another type of nanogenerators, that is the pyroelectric nanogenerators. Okay. So pyroelectric nanogenerators are basically when waste heat is converted into electricity, then that is the pyroelectric nanogenerator. So basically, we are harnessing the temperature or harnessing the heat energy, that is waste energy, which is a very rich source of energy and it is very much available everywhere. So that waste heat, it is a rich source of energy that could be harvested, and harvesting of waste heat would provide a prominent option for green and renewable energy. Okay, so the term thermoelectric and pyroelectric energy harvesting comes. We will be discussing what is thermoelectric and what is pyroelectric. So pyroelectricity, it is an ability of the material to generate an electric signal when it is subjected to thermal change. And if pyroelectric word, it comes from the Greek word pyro, which means fire. Okay, that so some basic points. Pyroelectric energy harvesting requires temporal temperature variations, that is time gradient. Basically, time gradient of temperature, basically variation of temperature with respect to time. In case of pyroelectric nanogenerator, it is temperature change with respect to time, whereas in the temperature change with respect to time, whereas in the case of here this one thermoelectric, it is also temperature change but with respect to space, depending on the area. Okay, so both of these we will be discussing. Whereas thermoelectric requires spatial gradient of temperature. It is time gradient of temperature and it is spatial gradient of temperature. Curie temperature, it is a critical point where the non-polar material undergoes a structural transformation. So it is also uh, crucial factor, that is the Curie temperature. It is the critical point where a non-polar material undergoes a structural deformation. So below Curie temperature, just a second. So below Curie temperature, material exhibits an intrinsic permanent electrical polarization, usually along a certain crystallographic axis. Recently, pyroelectric nanogenerators have developed to scavenge the thermal energy with time temperature gradient. So some of the very famous pyroelectric materials are zinc oxide, PZT, KNBO3, and PVDF. Okay, this energy harvesting is used to power low energy devices such as body worn sensors, wearable electronics. Okay, so what is pyroelectric effect? At thermal equilibrium state, the localized charges are shielded by the free charges with same quantity but opposite signs, so that there is no net electricity produced. In the ferroelectric materials. So when the crystal attached to an external circuit, electric current, there is rearrangement in the surface charges. So as you can see here, at thermal equilibrium state, the localized charges they are shielded by the free charges, and they free charges with same quantity but opposite sign, so they are like there is no net electricity, they are all in the random there is no proper orientation, they are randomly distributed, but when you attach an external electric circuit, these charges get aligned, the polarization takes place, and due to this polarization, when a temporal temperature gradient is applied on the crystal, the arrangement of the surface charge results in flow of electron in the circuit, which results in current generation. So basically, what happens? A pyroelectric nanogenerator, it is a energy harvesting device which converts the external thermal energy into electrical energy by using nanostructured pyroelectric materials. Okay, so pyroelectric crystals are the materials which, when heated, the atomic structure crystal lattice changes and they exhibit a potential difference at both ends. So what will happen if suppose these are the pyroelectric crystals. So when they are heated, the atomic structures within them changes, their lattice structure changes, and due to which polarization of the charges takes place, potential difference occurs on both electrodes, due to which due to the potential difference, current flows in the external circuit. The whole crystal is changed from one temperature to another, and the result is the temporal voltage across the crystal. So now coming on to the mechanism, it is of two types: primary pyroelectric effect and secondary pyroelectric effect. So primary pyroelectric effect, it describes the charge produced in a strain-free case. Okay, so there is no change in the dimensions. Strain-free case means there is the dimension of the crystal on heating remains same. Upon under a fixed temperature, there will be no output of the pyroelectric nanogenerator. If the temperature does not change, if suppose there is a pyroelectric crystal which is kept at the room temperature, then there will be no output. But if we increase the temperature, the increase in temperature will result the electric dipoles oscillate within a large degree of spread across the around their respective aligning axis. And if the nanogenerator is cooled instead of heat, and it is not like you need to heat only, you can cool also. Only the change in the temperature is required. It is not heating, it is basically change in the temperature. So if the nanogenerator is cooled instead of heated, the spontaneous polarization will be enhanced since the electric dipoles oscillate within the small degree of spread. So basically, if you heat, then the electric dipoles will oscillate within a large degree of spread. And if you cool, then it will oscillate within a small degree of spread due to the lower thermal activity. Obviously, when you cool, the thermal activity when you cool, then the motion of thermal activity is reduced. Okay. Now, secondary pyroelectric, it describes the charge produced in the strain induced by the thermal expansion. So here in this case, it is a strain-free case. No thermal expansion or deformation is there. But in the case of secondary pyroelectric effect, if you heat, then the strain which is induced by the thermal expansion or shrinkage, then that is converted into electricity. Okay, the secondary pyroelectric effect dominates the pyroelectric response in zinc oxide, cadmium sulfide, and some other woodside type materials. The thermal deformation can induce a piezoelectric potential difference across the material, which can drive the electrons to flow in the external circuit. So, what will happen? The thermal deformation will induce a potential difference, and that potential difference will drive the electrons to flow in the external circuit. Okay. The output of the nanogenerator is associated with the piezoelectric coefficients and the thermal deformation of the materials. So, in this case, it is strain free, but in this case, due to the thermal expansion, what is happening? Pyroelectric as well as piezoelectric, both the effects are working together. Piezoelectric, that means when strain comes, piezoelectric will come. Okay. So, due to the heating, also heating as well as the piezoelectric strain will the both will contribute to the generation of electricity. Okay. Now, pyroelectric coefficient, what is it? It is a pyroelectric coefficient. It is pyroelectric effect of a pyroelectric material is characterized by pyroelectric coefficient. It is a parameter to measure pyroelectric efficiency of the material. With a small change in the temperature, that is dT, the variation induced can be given by delta P equals to small p delta T, where P is the pyroelectric coefficient, and it is a vector, has three non-zero components. Pm equals to del Pm by del T, where M is 1, 2, 3. And the sign of pyroelectric coefficient is determined with respect to the pyroelectric effect of pyroelectric crystals. Pyroelectric axis of pyroelectric crystal mean the sign of piezoelectric effect, it will be according to the piezoelectric axis of the piezoelectric crystal. Sorry, I guess it is typed wrong. It is pyroelectric axis of the pyroelectric crystal. Now coming on to factors which needs to be considered in selecting material for pying. So it is, in short, it is called pyroelectric nanogenerators. They are called pying. It should have high figure of merit. What it is, we will be talking in further. High dielectric constant, high environmental stability, high availability of the material, low cost, high durability. So the pyroelectric materials, basically ferroelectric, they are this whole universe is dielectrics. Some materials in the dielectrics are piezoelectric materials. All these piezoelectric materials are pyroelectric materials, and all these ferroelectric materials are pyroelectric materials. So this is basically a universe where dielectrics is the main part. Out of them, some of the dielectric materials are piezoelectric materials. All the piezoelectric material, these all pyroelectric materials are piezoelectric materials, and all ferroelectric materials are pyroelectric materials. Okay. So basically, these are some of the materials which are some of the famous pyroelectric materials are triglycine sulfate, polyvinylidene trifluoride, that is PVDF, which is a very famous pyroelectric as well as triboelectric material, lithium tantalate, strontium barium niobate, perovskite structures, lead germanate, gallium nitride, and zinc oxide. So coming on to triglycine sulfate. So it is coming with this formula NH2CH2COH whole thrice H2SO4. It is formed by evaporation of an aqueous solution of sulfuric acid which is containing a greater than threefold excess of glycine. Okay, so glycine and sulfuric acid, it is mixed and it is evaporated at 45 degrees C to form this triglycine sulfate. The crystal structure consists of SO4 2 negative, 2 NH N positive, NH3 positive, CH2COH, G1 and G2 in the crystal structure diagram. So this is G1 and G2, and G3 species held together by hydrogen bond. They have several serious problems in practical applications such as water solubility, hygroscopic nature, and fragility. So they are used as pyroelectric materials, but they have they have serious problems such as water solubility is an issue. Hygroscopic in nature, that is, it absorbs moisture from the atmosphere, that is also a problem, and it is fragile, that is, it is brittle. Another material is polyvinylidene difluoride. PVDF molecule has a repeating unit CH2, CF2. Okay, so this is CF2, then CH2, CF2, CH2. This is the alpha phase and this is beta phase. So beta phase is active, but active and most used, but alpha phase it is not used. In this case, the CH and the electrically polar. So this is CF is electrically polar. As you know, fluorine is highly electronegative. So this is a electrically polar bond, and the electrically polar CF bond can take up a number of stable configurations depending on the processing of the polymer. So alpha phase of PVDF is formed from slow cool melts in which the bond are in a transgauche, transgauche, transgauche configuration, and the molecules are stacked to form a non-polar unit cell. Whereas the alpha phase, when it is stretched and electrically poled, it becomes beta phase, in which the molecular groups are all in trans configuration. They are all in trans state, whereas here one, then two, two, two. So these are in transgauche state. So they are assembled to form a polar unit. So in the alpha phase, it is non-polar due to trans-gauge configuration, whereas this beta phase, due to all trans configuration, it is polar unit. So we need polarity basically. So that's why beta phase is mostly used in the Steng and Peng and Pying like fabrication. Okay. Pyroelectric coefficient of PVDF are lower than those of TGS family materials, but this PVDF is quite widely used right now. Since this is also a polymer, so it also adds benefits of like flexibility, lightweight. So it is widely famous among the researchers. Lithium tantalate. Lithium tantalate is one of the most important pyroelectric materials. Its crystal structures consist of layers of oxygen ions, approximately hexagonal close packing with lithium and tantalum ions occupying two-thirds of the octahedral interstices between the layers. This material is one of the most stable pyroelectrics with a very wide temperature range of operation. Disadvantage is that it has high thermal diffusivity, which reduces the minimum resolvable temperature difference at high spatial frequencies when it is used for array application. Just a minute. So, coming on to the next material, that is strontium barium niobate. You just need to like memorize the formula and basically the crystal lattice of these structures. That would be enough. It's a lot of chemistry. I'm also not of chemistry background, so it's a I can understand. So you just try to like learn the formula of these formula and name of these materials. Like they may ask which of them is a pyroelectric material, so they may give in that way. So you may learn that on that, and as well as try to memorize the crystal structure. It is octahedral or tetragonal or pentagonal, that kind of thing. Okay. So strontium barium niobate, that is SBN, shows tetragonal tungsten bronze structure. So they may ask like strontium barium niobate, what kind of structure it has. So you need to memorize this. NBO octahedra make up the crystal framework, and among NBO octahedra there are two tetragonal sites A1 and four pentagonal sites A2. A1 is Sr2 positive ion and A2 is Sr2 positive or Ba2 positive ion. Sr2 positive and Ba2 positive ions randomly occupy 5 A sites, including A1 and A2. Now coming on to perovskite structure, ferroelectrics with perovskites have a general formula. This is an important one. PVDF is important. Perovskite is important, so try to memorize it. AbO3 kind of formula. It is rhombohedral lead zirconate or tetragonal lead titanate group of perovskites have been extensively studied. So these are some of the famous perovskites which are widely used as pyroelectric materials. Okay. PBTI, PBZRO3 or PBTIO3 dopants are used to improve the pyroelectric effects. Means sometimes some dopants also you can be used can also are also used to improve the pyroelectric effect. And these perovskites they have high Curie temperature of 490 degree. That is why a high polarization rate and deposition of thin film layer is preferred than machining from bulk to make a device. So we just need a small thin film for fabrication of a good pyroelectric nanogenerator. Okay. So lead germanate is a hexagonal ferroelectric material. It has a Curie temperature of 178. It can be doped with barium to replace lead. As you know, lead is very like poisonous. So it is a like need of the hour to replace all the places where lead is required to replace it with some other thing. So it is a good thing if you can dope barium to replace lead or silicon to substitute germanium. Pyroelectric properties of single crystals of both PB5G3011 or PB4.7 barium point 3, germanium 3 and O11 have been studied. Both pure PGO and doped one can be made into thin films. So all these materials they if they can form thin films, that is also an additional advantage. Okay. Gallium nitride, it is a woodside structure crystal. It is a natural pyroelectric with polarization in the C axis and it exhibits a strong pyroelectric effect above 300 degrees C. And it finds application in high temperature environments. Okay. Then zinc oxide, it is also quite famous. It is a woodside structure, natural pyroelectric crystal with polarization in the C axis. Most applications utilizing zinc are as the primary material use it in the thin form. So it is also an advantage. It can be easily used in a thin film form. Zinc oxide thin film has exhibited a conversion of thermal radiation 10 times larger than gallium nitride. Okay. So these are some of the applications of pyroelectric nanogenerators, that is electricity generation from waste heat, then sensors, powering small devices, infrared thermometers, infrared thermal imaging. Okay. So now coming on to the next part, that is the thermoelectric. So as I told, pyroelectric, they convert electricity, they convert temperature to electricity on the basis with respect to time. Whereas in the case of thermoelectric, it is temperature with respect to uh, space. So, waste thermal energy is one of the largest sources of inexpensive, clean, and fuel free energy available. Thermoelectricity is a promising technology in the direct conversion of waste heat into electrical power. So, thermoelectricity refers to a class of phenomena in which a thermal difference creates an electrical potential or vice versa. At atomic scale, an applied temperature gradient causes charge carriers in the material to diffuse from hot side to the cold side and thus inducing a thermal current. Thermoelectric power generator is a device that converts the heat energy into electrical energy based on the principle of Seebeck effect. So it basically works on three effects: Seebeck effect, Peltier effect, and Thomson effect, which we will be discussing. So in a thermoelectric material, there are pre-carriers which carry both charge and heat. Okay. So the device consists of a thermocouple comprising a p-type and n-type material connected electrically in series and thermally in parallel. So these are two materials. That is, one is the n-type and another is p-type. They are connected electrically in series. In terms of electrical connection, it is connected in series. As you can see here, it is connected in series and thermally in parallel. And in case of thermal, from here you are providing heat or you are heating it temperature. So here they are connected in parallel in case of temperature, and in case of electrical it is connected in series. Okay. So heat is applied in one side. If suppose you are applying heat here in one side of the couple and rejected from the opposite side, and it is rejected from here, an electric current is produced proportional to the temperature gradient. So the temperature mean extra temperature, that is delta T. With respect to that, a temperature gradient is formed here. An electric current is produced proportional to the temperature gradient between the hot and the cold junction. So, in comparison to both these junctions, the temperature difference with the respect to the temperature difference of an electric current is produced. Nanomaterials with higher performance are more attractive than their bulk counterparts. So basically here they are saying ki if you are taking suppose zinc oxide, if you are taking zinc oxide in bulk, for example, zinc oxide is thermoelectrically active and you are using bulk of zinc oxide, that is not that efficient. Instead, if you use zinc oxide nanowires or zinc oxide nanomaterial, then that will give a better performance compared to the bulk counterpart. Okay. Coming on to the working principle, it works on three principles: Seebeck effect, Peltier effect, and Thomson effect. So, Seebeck effect, it is basically the phenomena in which temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference. Suppose these are two semiconductors, two different semiconductors. For example, if suppose you take one P type and one N type, so both of them are different semiconductors. So in this, a temperature difference between two dissimilar conductors, if there is a temperature difference between them both, they will produce a potential voltage difference between the two substances. This temperature difference will produce a voltage difference between the two substances, two conductors. The voltage difference developed can be derived by using this formula, where Sa and Sb are the Seebeck coefficient of the material A and B, as a function of temperature, and T1 and T2 are the temperature of the two junctions. Okay. Now, other is the Peltier effect. It describes the thermoelectric material that can convert electrical energy into thermal gradient. I mean, in this case, this temperature, this Seebeck effect is converting the temperature difference into electrical current. I mean, temperature difference is producing a voltage difference, whereas in this case, a voltage difference can generate a thermal gradient. Okay, so when a current flows through a junction composed of different materials A and B. Heat is generated at the upper junction at T2 and absorbed at the lower junction at T1. So that an electric current, if an electric current is passed through two different materials, then temperature gradient between the two materials is created. Okay, so the Peltier heat, that is Q naught, absorbed by the lower junction per unit time, it is given by this formula, where pi A and B are the Peltier coefficient of material A and B, and I is the electric current. So whenever current passes through the circuit of two dissimilar conductors, depending on the current direction, either heat is absorbed or released at the junction of two conductors, depending mm, on the material of the both the conductors. One conductor will absorb heat and other will release heat at the two junctions of the conductors. Okay. Now coming on to the third effect, that is the Thomson effect. Any current carrying conductor except for a superconductor with a temperature difference between two junctions either absorbs or emit heat depending on the properties of the material. Okay. So if you take a current carrying conductor, if a current density J is passed through the homogeneous conductor, the heat proportion Q per unit volume, it is given by this formula. If suppose there is a conductor, except for a superconductor, if there is a current carrying conductor, if the current is passed through a conductor and both the junctions have a temperature gradient, any current carrying conductor except for a superconductor with a temperature difference between two points either absorbs or emits heat. Basically, that is relatable to this Peltier effect and Seebeck effect, that any current carrying conductor through which current flows, then there will be temperature difference. Temperature difference will definitely be there. Either it will cool or it will heat depending on the property of its material. Okay. So here, as we are saying that one conductor will absorb electricity and other will absorb heat and other will emit heat. So that means one conductor will heat up and other conductor will cool. So on what basis it will cool and heat, that is defined by Thomson effect. Depending on its material property, that is the resistivity of the material, then Thomson coefficient and temperature gradient along the wire. Okay. Now coming on to criteria of thermoelectric materials for high efficiency. One criteria is the figure of merit. So the performance of thermoelectric effect depends on the figure of merit, that is ZT. It is given by this formula where T is basically the average temperature average temperature, and ZT value, it should be between 3 to 4. It is desirable value, but till now researchers have not attained ZT value above 3, but they need for a good thermoelectric material, they are estimating that if a value between 3 to 4, then it is good, but till today the reported values are only in the range of 2 to 3. Okay. And device efficiency, the efficiency of a thermoelectric device for the electricity generation, it is given by energy provided to the load upon heat energy absorbed at the junction. So this is the output to input. Okay. So this figure of so the main concern of thermoelectric material is to increase its figure of merit. So it basically depends. It is a basically a coefficient which depends on a Seebeck coefficient, electrical resistivity, thermal conductivity, and temperature. Okay, so all these factors are responsible for making a material. Mean all these coefficients should be good for in a material so that it should have a good figure of merit, and that will make a good thermoelectric material. Now, selection of material for thermoelectric nanogenerators. So it should have high Seebeck coefficient, low electrical resistivity, and low thermal conductivity. Okay. So thermoelectric materials, there are various nanomaterials there are various materials which have thermoelectric property. Single phase materials are also there. These are some of the single phase materials. Then some of the anisotropic chalcogenide materials, then some isotropic chalcogenide compounds, and some oxide thermos electric materials. Okay, so there are various materials, various classes of materials which are basically having thermoelectric property and can be used in thermoelectric nanogenerators. Now, thermoelectric effect for waste energy harvesting. Two main applications can be expected by using thermoelectric effect. Seebeck effect thermoelectric nanogenerator and Peltier effect thermoelectric nanogenerator. Two types of commercially available multi-couple thermoelectric devices. Type A is basically designed. This is type A and this is type B. So type A, it is basically designed for cooling applications with large inter-thermo element application separation, and type B for power generation with much dense structure, very small thermo elements, inter-thermo element separation to increase the power density of the material. Okay, and this is basically another thermoelectric nanogenerators, which are a kind of thermoelectric nanogenerators. So they are basically based on thermoelectric nanomaterials. So basically, instead of using whole bulk material, using thermoelectric nanomaterials and is a better idea, and they can realize direct conversion from thermal and electric energy. Okay, so tags can be divided into two categories, including rigid and flexible tags, and they are mainly used in fields of power generation, heating, and refrigeration and temperature sensing. So basically, here they are saying that instead of using bulk material, using a nanoparticle, nanomaterial, thermoelectric material, when using all these materials, they are not nanomaterials. Okay. They are not nanomaterials, but instead of using these materials, if you use nanomaterials, then the performance of the material will be very much improved. Okay. Nanostructured thermoelectric material. These are some of the nanostructured thermoelectric materials. These are all of these are nanomaterials which can be used and increase the efficiency of the your efficiency of your thermoelectric nano generator. Advantage: it has no moving parts, so it is noise and vibration free. Their overall volume is relatively small. They exhibit very high reliability and they are scalable and no position dependent. Low energy conversion efficiency rate is there, that is a disadvantage. Slow technology progression, there is not much work going on in this field till now, so it is very slow progressing. High cost and requires relatively constant heat source. Okay, these are some of the applications. Just a second. Another device is the electromagnetic generator. So basically, the vibration energy can be harvested. Electromagnetic force is converted. If electromagnetic force, some kind of magnet is there, then the electromagnetic force can be converted into electricity. So that is basically the electromagnetic generator. The vibration energy can be harvested from ambient micro vibrations from body activities and from mechanical activities equipments. So basically here vibration energy is converted into vibration energy can be harvested into different uh, kind of can be harvested into electrical energy. So they come under electromagnetic generators. The vibration energy harvesting devices, they are electrostatic, electromagnetic, piezoelectric, triboelectric. All of these are vibration energy harvesting devices only. Okay. But the electromagnetic harvesting device have lower production cost and longer lifetime. Okay. They have lower production, mean electricity produced is less, but they have a very longer lifetime. Electromagnetic methods include linear generators or rotary generators. In rotary type generators, linear vibration motion is converted into rotary motion using screws, chains, or gears that we will be studying. Okay. Now, linear magnetic generator, it consists of an armature, stator, case. As you can see here, this is the armature, then stator, and then case. Okay. And there it is a magnet from which the electromagnetic where from where the magnetic field will be generated, and that magnetic field will be converted into electric field. Okay. So the that magnetic field will generate an electric field, and electrical energy will be generated. Okay. The armature consists of a permanent magnet core and shaft, while the stator consists of an electromagnetic coils. A a neodymium a neodymium ferrite magnet is used for the permanent magnet. Non-magnetic stainless steel is used for shaft, and steel 1010 is used for the core. Okay. Tension and compression springs were used to apply the resonance phenomena to the armature. So here simply, he, this is the working principle. The electromagnetic generators works on the principle of electromagnetic induction, which is Faraday's laws of induction. Faraday's laws of induction state that the electromotive force around a closed loop or around a closed path is equal to the negative of the time rate change of the magnetic flux enclosed by that path. So EMF equals to minus the minus that it is basically the electromotive force. It is equal to the negative of the time change of the magnetic flux. So this is the magnetic flux. So it is the negative change with respect to time of the magnetic flux. So induced EMF, it depends on the magnetic property, spring mass property, coil property, and power processing circuit. Okay. So the magnetic flux density is a significant parameter in designing micro generator. Rare earth magnets produce a strong flux density and suitable for this application. So these are some of the materials which can be like this is neodymium iron boron. It is a magnet. It is a natural magnet. It is known as the most powerful magnetic property per cubic centimeter and able to operate up to 140 degrees C. Okay. And these are some other materials which are the rare earth materials. They are also good magnets with less power and less expensive compared to this one. Okay. So these are some of the natural materials which have this electromagnetic power, electromagnetic force. So we can use the electromagnetic force generated by these materials to convert them into electrical force. Okay. Spring mass property. So this is the magnet property. If you use materials like these, then spring mass property, spring mass system is referred as the system that provides oscillation for the magnet in order to achieve flux cutting mechanism and induce certain EMF. Okay, so this is the spring and mass. They are responsible for the oscillation in the like in this electromagnetic nanogenerators. So the spiral shaped spring with lower spring constant and lower stress concentration produces large displacement when oscillated. Mean as much mean the displacement during oscillation should be more so that thus maximizes the flux cutting rate and induces higher EMF. Okay, so the for that purpose, large displacement should take place so that maximum flux cutting rate is there and higher EMF is induced. This spring is suitable for low frequency power generators. Cantilever or paddle or beam springs are also preferred sometimes. Okay. Coil property. Coil wire or coil are widely reported as induction coil used in micro generators. So either the material of the coil is also very important. So either coil wound copper coil or electrodeposited copper coil is used in reported micro generator device. So mostly the copper wire is used for the coil. Okay. Sometimes gold has also been used as coil material in fabrication process, but copper metal as coil is more commonly used since gold means since copper has better conductivity and more cost efficient. Okay. Power processing unit. The power generated from the ambient vibration is going to be a time varying voltage. Okay.
Ma'am,
So this vibration may be reliable or periodic as the ambient vibration is non-deterministic and the generated voltage must be regulated to a certain level in order to maintain a specified performance level.
ma'am, what is the difference between
Coming on to
the
the advantages of this electromagnetic nanogenerators, it works at all types of weather. It is easy in construction and safer to use and high efficiency at high frequency and easy to scale up. Okay. But the strength of the permanent magnets, the strength of the magnet is a problem. It decreases with time, and cost increases with increase in strength of the magnet. Because if we need to change the magnet or increase the strength of the magnet, then it is very costly. Due to hysteresis loss in the core, heat will be evolved. Due to this, heat efficiency of the permanent magnet will decrease. Okay, low output for smaller devices. Now coming on to some of the conventional energy resources. Till now, we have discussed in the first class, you might know that we have discussed that some of the conventional and non-conventional techniques we need to discuss, which we in the initial classes we discussed in short, but they needs to be discussed. Okay, so as you know that we have discussed solar energy in detail, this nanogenerators topic is over. So now moving on to the conventional source of energy and some of the non-conventional energy sources also. So we have clearly discussed in solar energy in detail, but these few more energy sources are left, so we need to discuss them. So, starting with that, energy broadly means the capacity of something. So basically, based on the sources, there are two type of energy resources: conventional source of energy, and non-conventional source of energy. So conventional sources are basically which can be exhausted, but non-conventional are those which are like which cannot be exhausted or basically renewable energy sources. Okay. So the conventional source of energy are also known as the non-renewable energy sources because they are limited in quantity like fossil fuels, and non-renewable energy sources and sorry non-conventional source of energy, they are also called as renewable energy sources because they are not exhaustible and they are available to us in a mean in infinite amount. So the conventional sources, the first one is a thermal power plant. So basically, thermal power plant converts the heat energy of the coal into electricity. So simply, what you might know that coal is burnt in a furnace, which converts the water into steam, and then that steam is used for the turning of the turbine, and the which is coupled to a generator. or that turbine is coupled to a generator which is used for the generation of electricity. Okay. So in thermal generating stations, coal, oil, natural gas, all of them are used as source of energy. Okay. So the main components of a thermal power plant is the energy source is the coal, natural gas, diesel. Then boilers, the fuel is burned in the boiler in the furnace to produce steam, and the steam generated in the boiler is used to run the turbine, and then the turbine it is coupled to the generator which converts the mechanical energy into electrical energy. Okay, and after that the steam which is remaining, just a second, remaining which is passed out after moving the turbine, the steam after passing through the turbine it is condensed in a condenser, and the water is then supplied to the cooling tower where it is cooled and it is further recycled back to the furnace or the steam boiler where then it is again converted into steam. So the cycle goes on. Okay. Now, where the nanomaterials are used in this thermal power plant? So, MOF materials and that subsequent to ceramic like structural processing afford a material displaying exceptional values for carbon dioxide or nitrogen selectivity based on ideal absorbed solution. So basically, where these nanomaterials are used in thermal power plants, basically to it is used for the absorption of different gases. Okay, so MOF-based materials are quite famous for the absorption of carbon dioxide or nitrogen. And okay, the nano TiO2 it acts as a catalyst to improve sulfur removal efficiency with dry scrubbers. So in the dry scrubbers for the removal of sulfur, this nano titanium dioxides are used. Then nanoparticles with high thermal conductivity, that is alumina, copper oxide, graphene, CNTs, they are used in the disposed in the heat transfer fluid like water to enhance their heat transfer efficiency. Okay, so now nanomaterials like CNTs and calcium oxides they are also used to absorb the CO2 gas which is emitted from the thermal power plant. Okay, so the advantage is fuel use is quite cheap. These fossil fuels they are cheap but less initial cost as compared to other generating stations. It can be installed at any place irrespective of the existence of coal. The coal can be easily transported to the site. Then disadvantage, prime contributor to CO2 emission. It is like contributing to the CO2 emission. Large amount of coal and water is required. There is a like large amount of water is also required, and as you know there is shortage of water. Maintenance cost is very high and overall efficiency is lower than 30%. Okay, now coming on to another type of energy, that is the nuclear energy. It is a powerful source of energy and generated during interaction between the nuclei of atoms. So there are two phenomena which are taking in a nuclear power plant for the generation of energy. One is used for the generation of energy, but other cannot be used for the generation of electricity. Okay, but sun is the natural example of nuclear energy source. How? Because the energy that we are getting from sun, basically in the form of heat and light, it is coming due to the nuclear fusion reaction which is taking on the surface of the sun. So basically, we will be discussing what is nuclear fission and nuclear fusion. So basic principle of nuclear power plant is to obtain extreme heat energy which is used to boil water and convert it into vapor. Then vapor is used to rotate the turbine, and finally mechanical energy is converted into electrical energy. So the same phenomena they are using. A lot of heat they are generating. That nuclear fission reaction is generating a lot of heat which is used for the boiling of water and generation of steam, and then that is used for the that steam is used for the generation of electricity by turning the turbines. Okay. So the what is nuclear fission and nuclear fusion? So in the case of nuclear fission, this is basically the fuel uranium-235 which is normally used in the nuclear power plants. So this nuclear fission, it is the nucleus of a heavy radioactive element like uranium or thorium. It splits into smaller nuclei. This nucleus of this U-235, when it is bombarded with a neutron, it splits into two lighter nuclei and releasing a large amount of energy which is further used for the boiling of water. And a huge amount of heat is generated in this process, which is used in nuclear power plant to generate electricity. So this nuclear fission is used for the generation of electricity. But nuclear fission, when nuclear fission reaction involves a combination or fusion of two lighter elements to form a heavier element. This is the opposite of this one. Okay, here heavier breaks into smaller lighter, whereas here two lighter elements combine. That is, suppose deuterium and tritium, they fuse to form helium and gives out a neutron and giving a very large amount of energy. Okay, this so to form a heavier element and releases uncontrollable energy. This energy is uncontrollable, therefore it cannot be used to generate electricity, unlike fission reaction. So sun's energy, it is generated by nuclear fusion reaction. The heat and light that we get from the sun is all due to the continuous reactions going on inside it. Okay. Where are the nanomaterials used? Additional 5 to 10%, addition of 5 to 10% of uranium dioxide nanocrystal powder to traditional coarse powder allows to decrease the sintering temperature. So, mean for the sintering, there is a lot of temperature, very high temperature is required. So, if we add at least like amount of 5 to 10% of this nanocrystal uh, in the nano in the nuclear reactor, then the sintering temperature can be reduced. To set up the radiation damage stability of fuel element, jacket material was suggested to strengthen a heat resistant ferrite martensite steel by Y2O3 nanocrystalline powder. So basically, these nuclear power plants, they are very dangerous places. Like if any reaction goes uncontrolled, then radiation can leak and it can lead to accidents. So for that purpose, all these reactors and reactor jackets, they needs to be very very strong. So to improve that property also, Y2O3 nanocrystalline powder is used. MWCNT are an effective sorbent for europium, americium, and thorium, and the sorbent after nuclide sorption is very stable due to the strong complexation of sorbates on the MWCNT surface. Nanocrystalline silicon carbide or Ti3Si C2 alloys are used for high temperature reactor materials. Okay. Now advantages: produces large amount of energy, low harmful emission, mean it does not release carbon dioxide. Then high reliability, relatively operating low cost. It is it is a non-renewable energy source. That is a disadvantage. It will end one day. Radiation from nuclear material is large. Difficulty in storage of nuclear waste and nuclear power plant accidents are also a like threat. Now coming on to non-conventional source of energy. Another non-conventional source of energy, that is wind energy. Wind are horizontal movement of air from high pressure area to low pressure area. Wind energy is the kinetic energy associated with the movement of large masses of air. It is clean, cheap, eco-friendly, renewable source. Wind is utilized to generate electricity with the help of a wind turbine. So moderate to high speed wind, typically 5 meter per second to 25 meter per second, are considerable favorable for most wind turbines. So how to convert wind to electricity? It is an indirect form of solar energy basically. Wind results from an unequal heating of different parts of the earth, causing cooler dense air to circulate to replace the warmer air. For example, on the seashore, sand gets heated more than the water, so the air above shore is becomes hot and moves up, whereas the denser air, less hot air above ocean, it moves towards the seashore to replace the lighter air, and that causes the movement of wind. Okay. Higher wind speeds at seashore produces energy increase from 10 to 20% compared to ground installations. Okay. So efficiency depends on the number of blades in windmill. More number of blades, higher efficiency. Now selection of material for windmills. Low weight to mean wind that blades windmill should have low weight to reduce gravitational forces, high strength to withstand wind force and gravitational force of the blade, and high fatigue resistance to withstand cyclic load, and high stiffness to ensure stability of the optimal shape. Where nanomaterials are used in windmills, so composite materials are used for the wind turbine blades, fiber and reinforced polymers, because they are like these wind turbines, they are open in the atmosphere, then moisture is there, then rain, cold, all environmental problems are there, which may lead to the corrosion and degradation of the turbine blade material. So, composite materials are used. That is the fiber reinforced polymers. Variation in fibers, polymer concentration gives the combination different properties. Then CNT is dispersed uniformly in the resin offers advantage like high stiffness and toughness compared to pristine resin. Their properties and performance are directly related to size, structure, and interfacial interaction. CNT tend to agglomerate due to the strong bonding between the layers, which leads to poor dispersion and instability. Mean during the formation of the composite, the nanoparticles should be dispersed within the polymer matrix very nicely. For that, various techniques are used, such as sonication, surface modification, covalent functionalization. Means if the nanoparticles does not disperse properly within the polymer matrix, then the properties of the polymer, then the properties of the composite will be degraded to even more than the nascent polymer. Okay. Now, advantage, no air and water pollution, completely sustainable, fuel is free, low operating cost, and disadvantage is damage of local wildlife because all these windmills they are standing on like seashores or mountain areas where there are lots of trees needs to be cut, so that is basically a damage to local wildlife. Large overall land take, there is a lot of land required, and electricity production depends on the force of wind. Okay. Coming on to the tidal energy or tidal power can be defined as the energy that is the result of moon and sun's gravitational influence on the ocean. So tidal power, it is similar to the hydroelectric power as it makes use of moving water to spin a turbine to produce electricity. Height differences between the high and low tides create pressure difference between the turbine blades, which is used to run the turbines. And the tidal energy, it is a renewable source of energy. So basically, what happens, the difference in the waves in the ocean, they are used to move the turbines of the turbines which are coupled with a generator to generate the electricity. Okay. Where the nanomaterials are used, the simplest concept for a tidal turbine is a machine similar to a wind turbine but typically with shorter, stiffer blades. It is due to the difference in density between the water and air that complex loads that tidal blades experience. Okay. Anti-corrosion coating is required on the tides since they are completely underwater all the time, like nano, WC, and like tungsten carbide or cobalt are majorly used. Advantage, it is a renewable source of energy. Tidal power is environment friendly and tidal currents are highly predictable because they are like highly predictable mean like it will come twice, at least twice a day it will definitely come. Then long lifespan, then tidal power plants needs to be constructed close to land. That is a disadvantage. And installing and maintaining is expensive and spinning blades may kill marine wildlife. Coming on to another renewable energy source, that is the geothermal energy. So the word geothermal comes from the word geo, that is earth, and thermal is heat. So basically generating energy from the heat, uh, that is the energy from the heat of the earth. Basically, the it is its source lies 6,500 kilometers beneath the earth surface, contain a surface core containing hot magma. So surrounding the core is the mantle and outer layer is the crust. So basically we need to harness the heat energy of this hot magma. So what we do, we simply install pipes inside the earth from which from one side you like how it works, hot water is pumped from deep underground through a well under high pressure. So we pump water from one side which get under hot water is pumped from deep underground through a well under high pressure. When the water reaches the surface, the pressure is dropped, which causes the water to turn into steam. And then this steam spins the turbine, which is connected to the generator that produces electricity. So the steam cools off in a then further the steam is cooled off in a cooling tower and then condensed back to water, and the cool water is pumped back into the earth again. Okay. Where nanoparticles are used? high heat retaining properties of the I mean, the water can dissipate, heat can dissipate from when water is coming from below the earth to the surface, then also what heat can dissipate. So nanoparticles can be used for high heat retaining properties of the fluid. Nano coatings and nano composites for wear resistant drilling equipments, and nanomaterial coatings can be done to prevent corrosion. Okay. Advantage is independent of weather, less gaseous emission, low maintenance cost. Construction of power plant needs less space. Okay. But the disadvantage also comes that is not widespread source of energy, high installation cost. There is always a danger of eruption of volcano. Due to this procedure, there is always the threat or the disadvantage of the danger of eruption of volcanoes, and then geothermal site may run out of steam. So that's it for today. Oh, let's come to the assignment questions. There are few assignment questions. So the first question is, match the following group of piezoelectric materials based on unit cell structure in section A with their corresponding examples in section B. So anyone? I told you during when I was teaching this part that some of the examples you need to learn. Yeah. Sorry.
Ma'am, option D.
Anyone?
Option D.
Okay. Just a second. So the answer is, let me say, answer. I guess two of you have answered correctly. The answer is uh, B. This perovskite, as I told, it has this formula. So AbO3 type. This is the perovskite example. Then bismuth layer structure. This is the example which consists of bismuth. So this and pyrochlore group. It is this. Okay. So answer is B. Coming on to the next question, which of the following material will become negative when rubbed with other materials? I showed you two lists of materials, one that will attain positive charge and one that will attain negative charge in the case of triboelectric nanogenerators. So in them, in one of these is a negative, is a material which will attain negative charge. So which one is that? Anyone? Okay, the answer is Teflon. Deepak is right. Let me show you. Just a minute. It is aluminum polyamide 66 cotton and Teflon. Here. So here you can see this Teflon. It is showing very highly negative charge. This, whereas cotton will gain positive charge, aluminum will gain positive charge, and polyamide 66 will also gain positive charge. Okay. So the answer is Teflon. What is the meaning of fire in pyroelectrics? Okay. So pyre and pyroelectric means fire. It is a Greek word which means fire. I showed you. So it is. Okay. Hmm. Here it is. So pyre means fire. It is coming from a Greek word fire. Okay. So select the correct statement from the following related to primary and secondary pyroelectric effect. The primary pyroelectric effect describes a charge produced in a strain-free case. Whereas the secondary pyroelectric effect describes the charge produced in the strain induced by thermal expansion. Anyone?
Yeah. Both
The
are true.
correct answer is both the statements are true.
True.
So the correct answer is C. Let me show you.
Yes, madam.
Here, both the statements are true. That is, the primary pyroelectric effect, it is describes the charge produced in a strain-free case, and the secondary describes the charge produced in the strain induced by thermal expansion. Okay, so the answer is both statement 1 and 2 are true. Now, what is the limitation of triglycine sulfate in pyroelectric nanogenerators? Let us go to triglycine. Hmm. So here you can see the limitation of triglycine sulfate. The problem is water solubility is also a problem. Its fragility is a problem, and hygroscopic nature is a problem. Hygroscopic nature, mainly it is absorbs moisture in atmosphere. So basically all of these are the problem, all of these are the limitation of triglycine sulfate. Okay. So what is the main source for the formation of the wind?
Sun.
The main source is basically sun is the main source of formation of wind. How? As I told recently, that when uh, uneven heating of the land takes place due to the sun, then due to the difference in the density of the hot air and cold air, the motion of the air takes place. Okay. Why tidal energy is more powerful than wind energy? Let me go to the slide.
Second one, B option.
Tidal power is similar to. Hmm. It is due to the difference in density between water and air and complex loading that tidal blades experience. So basically, the simplest concept is of a tidal turbine is a machine similar to wind turbine, but typically with a shorter and stiffer blades. Why so? Due to the difference in the density of water and air. So water is more denser compared to air, so that's why the turbines of a tidal turbines are more stiffer and shorter. Okay, so it is due to the water is more denser than air. Which nanoparticle is commonly used in thermal power plant to improve sulfur recovery efficiency?
Option
Just now
D.
I told.
Car- Carbon
Anyone?
Option D.
nanotubes.
Ma'am, nano titanium dioxide.
I think option A,
B,
nanotubes.
B, B. Option B. Nano titanium dioxide.
C.
B, B.
No, the answer is nano titanium dioxide. Let me show you. Thermal power plant uses nano titanium here. Nano titanium oxide, titanium dioxide to improve sulfur removal efficiency with dry scrubbers. Okay. So the answer is B. Which phenomena cannot be used to generate electricity? Among these, which phenomena cannot be used to generate
Ma'am,
electricity?
fusion. Nuclear fusion.
Fusion, first one. Option A. Madam,
Anyone?
option A.
Nuclear fusion.
Just a second. Okay. Okay. The answer is correct. It is it is nuclear fusion. Since it produces a uncontrollable amount of energy, that's why it is not used for the generation of electricity. Okay. So here we are done with, sorry. The answer is correct. Thank you guys for your patience. Today has been a very long class. I hope
Oh,
I'm clear.
Thank you, madam.
okay, ma'am. Thank you, ma'am.
I guess someone asked some question.
No, no. Can we exit?
Basically, the difference between magnetic flux and magnetic flux density is basically the magnetic flux is the total number of magnetic field lines passing through a certain material, and magnetic flux density is per unit area. Mean magnetic flux lines passing per unit area. What is this MFD? It is linked with area, whereas MF not. Okay. Oh, someone answered. Okay. Thank you. So, any more questions? And you may ask, if you have questions, you may ask later also in the next class also. It's quite late, but if you want to ask, you can ask right now also. And if not, then we are done for today.
You can conclude, madam.
Okay. So, shall we leave? Shall I stop the class?
Yes, ma'am.
Yes, madam. Yes.
Most I try to cover I try to cover most of the topics, so that if you are not following sir's classes, then also it is beneficial for you, like one class enough for whole week. So I try to cover most of the topics, then also one two topics may uh, may be missing. So you guys need to look for the presentation of sir once before examination. But I am trying to cover at least 95% of the topics that sir is covering in his classes. So, and most of the questions of the assignment. So I guess that will not be a problem. And apart from that, you have any questions, then I am writing you my mail ID. You may mail me.
Madam, in 4 week course,
So this is my mail ID. Okay, so let's meet on next Friday.
Hello.
Thank you guys. I'm
Madam,
ending the class. Okay,
am I audible?
thank you.
Madam?